So where we were at last time, we explored this concept of non-interactive proofs. So up until last time, all the proofs we had looked at were interactive protocols between two parties who were exchanging messages in some way. And we sort of realized that this isn't maybe the most practical thing in a lot of applications. It's true, you can't have all of these active connections all the time. If you want millions of people to check a proof, this doesn't really work. So we started exploring this concept of a non-interactive proof instead. And the idea was that we're going to generate, the prover is going to choose their own challenge, but the prover has to do this in a way that means they somehow can't cheat, right? Because if they can choose any challenge they want, then of course they can easily produce an accepting transcript, even if they don't have a witness or even if the fact they're trying to prove is false. So the idea to do this was to use hash functions. In practice, we use something like SHA-256, and we get a result like on this second board here. We get sort of, once we do this transformation of the Schnorr discrete logarithm proof, we get this result. This is called the Fiat Chameleon transformation. And the question is, okay, it's not you could believe that this works, right? Because we're hashing all of this data together, and because the prover can't really choose this data. I mean, they can choose the commitment, but they certainly can't choose what statement they're supposed to be proving. They can't choose the group, and they can't really influence, even though they can choose the commitment. We assume by the properties of hash functions that this can't really influence the output. So we could believe that this is somehow a sensible thing to do. And the question is, okay, but this doesn't meet our definitions of soundness or zero knowledge, neither of them for that matter. So we started exploring how exactly we could do this. And we defined a weaker version of soundness called existential soundness. Before we talked about knowledge soundness, which was this definition that the prover knows some secret that they are using to produce a value. This weaker version, existential soundness, simply says that there exists, we can prove that there exists a witness, right? If the prover can produce a legit proof, there must exist a witness, but we don't make any claims about knowledge. There's no extractor happening here. And this weakening is going to allow us to define non-interactive proofs in a sensible way. And I showed an example of how this existential soundness is kind of enough for some applications. In this case, we're proving that two group elements have the same discrete logarithm with respect to two other group elements. And this, I sort of sketched how this would be useful in a context with certain types of encryption. And this is the setting that we're using. We're talking about a setting where what you care about, hello, I had some echo
Hey,
for a
sorry,
second.
we're testing things out in
No worries.
Moonlight Forest.
Well, welcome. So I was talking about
Thank
how
you.
we're in this setting where we care about existential soundness, right? Simply the fact that a witness exists is going to be good enough for us. And we want to prove that such a witness exists in zero knowledge. Okay. So my definition, I believe, is, oh no, it's fine. It's on the other board. Yes, very good. So in order to do this, to understand this Fiat-Shamir transformation, oh, the Fiat-Shamir transformation definition is gone. I'll just write that up again. So I'm going to omit some of the technical details because that's maybe a little bit distracting. But, so recall that a non-interactive proof was a non-interactive proof system, rather. Oops. So a non-interactive proof system is a pair of algorithms. These are probabilistic, but not interactive. They are just one-sided algorithm. We have one that is called Gen. It's going to take a statement, which we say lives in a set X, and a witness, which lives in a set W. and it's going to produce a proof, PS for proof space. The generation algorithm is probabilistic, and it's going to map statement witness pairs XW to proofs. Okay, and what the proof is going to depend on the particular protocol, like what type it is. It's just lives in some proof space, right? So for our Sigma protocols, the proofs you could think of transcripts, and we'll see if we look at if you compare to the non-interactive example I gave before, the proof is going to be the commitment and the response, right? The proof doesn't contain the challenge because the challenge is determined by the statement and the commitment. Okay, and then there was a check algorithm. This has to be deterministic. Okay, it's going to take a statement and a proof, and it's going to either accept or reject. Yes, this is a legit proof, or no, this is a bogus proof. And we say, I'm not even going to bother writing this out because it's really straightforward. We say it's existentially sound if any efficient algorithm that tries to generate a proof for a false statement has a negligible chance of passing check. Okay, so the misbehaving, the adversary here just gets a statement that is false or possibly false, and it's going to try to generate a proof. And we say it's existentially sound if given a false statement, the chance that check accepts it is negligible. Okay, in this sense, you could argue that it's an argument rather than a proof, but we won't make that distinction for now. Okay, and what was the Fiat-Chameleon transformation? We have a protocol, Fiat-Chameleon. We have a Sigma protocol. I call this pi. Remember that a Sigma protocol is interactive algorithms for the prover and specifier. Sigma protocol. And we define the Fiat-Chameleon transformation. It's a non-interactive protocol. Proof system. It's going to be parameterized by a hash function. H. And how do we define the non-interactive proof system? To generate a proof, the first thing we do is we run the Sigma protocol's prover. This needs a statement and a witness, and it's going to give us a commitment T. And we're going to generate the challenge, and that's just going to be at the hash of the statement and the commitment. This is going to be encoded in some way. So the canonical way to do this, right, is you take your statement represented as some bit string, you take your commitment represented as some bit string, and you concatenate them together. But the details of how you do that don't actually matter, as long as it's all consistent. And then once we've got the challenge, we're going to run the prover on the challenge, WTC, to get a response. And it outputs a proof, which consists of the commitment, commitment and the response. Okay. And how do we define the check algorithm? Well, this is really quite straightforward. It's just going to generate the challenge itself and ask the verifier if this is a legit conversation. So we set the challenge to be the hash of the statement and commitment, and we just output what the verifier says, given challenge, response, and commitment. Okay, so this is the Fiat Chameleon transformation, and this is how we're going to take a Sigma protocol and produce a non-interactive protocol. Any questions so far now that we're catching up? All right. So what we're going to try to do is argue that the Fiat Chameleon transformation of a special sound Sigma protocol is an existentially sound non-interactive protocol. So to do this, we sort of have to make sense of this hash function. We discussed last time how hash functions are kind of nebulous and not really well-defined theoretically. So the way that we'll model them is using the so-called random oracle model. And this is essentially, we're going to pretend that a hash function is a uniformly random function. Okay, so the idea is if you give it a value it's seen before, it produces the same value that it produced last time. Otherwise, it chooses a new totally random output and then gives you that output. And this is an idealization of what hash functions are supposed to do. Of course, hash functions don't actually do this, right? But ideally, this is how they behave somehow. So we're going to say, if we assume that the hash function that the Fiat Chameleon transformation uses is a random oracle, we can prove existential soundness, and we say that it's existentially sound in the random oracle model, the RAM. All right. So we're going to try to prove this, and it's going to be done with a reduction. Okay, so we're going to assume that there's some algorithm, A equals gen hash, and we assume that this can cheat in the Fiat Chameleon protocol. By cheat, I mean it can produce a proof for a false statement that nonetheless is accepted by check. And we're going to arrive at a contradiction. We're going to arrive at the contradiction, contradicting the fact that the Sigma protocol we started with was existentially sound. In other words, we're going to construct a cheating prover that can non-negligibly make the verifier accept in the Sigma protocol. Okay, so how are we going to do this? Well, we're going to start by, without loss of generality, we assume that our protocol that produces proofs of false statements at some point sets its challenge to be the random oracle output of X and T. This is without loss of generality, because if our algorithm somehow does it without doing this, well, we can just change the algorithm so that it queries the random oracle and then outputs nothing, okay? So we're thinking of the random oracle here as stateful, right? It starts with an empty list of associations, and then at some point you query it, and it adds to its list. So that way it knows what it's already output. And how are we going to construct our B assuming this? Well, A is in particular efficient, so that means B can run an instance of A, it can emulate A on its, if it's a Turing machine, it can just sort of emulate it on its tape, if you like. And at some point, we assume A is going to query the random oracle value X and T, where X is the statement, T is the commitment. Now, there's a subtlety here, which is that you can't define an algorithm that somehow knows which of A's outputs that it emulates is going to correspond to querying the random oracle in advance. It can't know this, right? This is I think this is a reduction to Rice's theorem even. So this is fine. We can work around this pretty easily. We say that, well, A queries the random oracle some number of times, right? In particular, some polynomial number of times, because it runs in polynomial time. And B is just going to guess which of these queries is supposed to be the one that generates the challenge. And what it's going to do is when its emulated instance of A makes that challenge, okay, so that's this challenge here, B is going to stop emulating A, and it's going to say, okay, now I'm going to talk to the interactive verifier, start my round in which I will cheat, okay? So B is going to choose, it's going to interpret A's query as a statement commitment pair, extract that commitment T, and send it as its commitment to the verifier. The verifier is now going to choose some challenge, and B is going to return that challenge to its emulated instance of A. Okay, so A is running inside B here. Now, if B correctly guessed which query was supposed to be the challenge as the random oracle evaluation of X and T, then, well, A, by definition, is going to produce a response that the verifier accepts. So if B correctly identified which emulated query was the challenge, was evaluating to the challenge, then, well, A is going to produce a response that works, B can send that response to the verifier, and the verifier is fooled. Okay. So now we just have this wart where B is trying to sort of guess which query was the right one. Well, the number of queries that the emulated instance makes is polynomially bounded. So B succeeds with some ratio 1 over a polynomial times A's success probability. But if A's success probability is non-negligible, dividing by the polynomial still keeps it non-negligible, so B still wins a non-negligible amount of the time. I use this phrase win. This is sort of a duality that we do in crypto, right? We think of a reduction as a game where the adversary is trying to cause some bad behavior. This is something that we're going to return to when we talk about zero knowledge. But does anyone?
Sorry, you said you think of the
proof? I guess it's more of a proof sketch, but yeah, go on.
You said you thought of the reduction as a game. Is that what you said?
Yeah. So what we're trying to do is we're trying to reduce existential soundness of. I have to be careful about how I say this. We're trying to reduce existential soundness of the interactive protocol to existential soundness of the non-interactive protocol, which means if I produce an adversary that breaks existential soundness in the non-interactive protocol, I can produce one that breaks existential soundness in the interactive protocol. So we think of this attempt to break existential soundness as a game, right? The idea is the adversary is playing a game against the verifier, trying to win, which means that it gets away with cheating. So yeah, it really is. It's just a reduction, and what I've done is I've just produced an adversary that can break interactive soundness, assuming I could break non-interactive soundness. But if it's a Sigma protocol that's existentially sound, then it's existentially sound. So we have a contradiction and we are done. Okay. Any questions? Okay. There's a little bit of subtlety here, so I want to make sure. All right. So we have soundness, yay. Now we want to talk about zero knowledge, which is a little bit harder. I'm going to go over to the first set of boards. So we want to somehow extend our previous idea of zero knowledge. How do we define zero knowledge for Sigma protocols, or sort of this interactive protocol more generally? Well, we said that if I can give you an efficient simulator that, if I give it a statement, can approximately match the output distribution of a transcript between the two parties, right? So the simulator can produce transcripts that are indistinguishable from the distribution of real transcripts. So the verifier could have just run the simulator on its own. So the eavesdropper could have just run the simulator on their own, so they didn't learn anything from the interaction. Okay. So what do we want to do? We want a simulator that, oops, I always do that. We want a simulator that if we give it a true statement can somehow produce proofs that match the output distribution of the actual prover, the proof generation algorithm. The problem is that this is nonsense. Okay, there's at least two things that go wrong here. So, okay, I'll start with the good news. Since the verifier does not interact with the prover acts entirely on their own. All we need is honest verifier zero knowledge, right? It's fine to assume that the verifier is honest because the verifier can't do anything anyway, okay? So the good news is that honest verifier is fine. We don't need to do any kind of argument about it being C simulatable or having certain niceness properties, being a sigma protocol, the challenge space being polynomial. We don't have to worry about that because, well, the verifier can't affect how the prover works anyway, so we can safely assume the verifier is honest. It's finite, is fine. The bad news is that this makes no sense. So we give the simulator a statement. We give the simulator just some random statement and it produces a proof. Well, it might be able to prove false statements. If we simulate given any statement, we might be able to produce proofs of false statements. Okay, that's bad because that would contradict existential soundness. And it gets worse because even if it only ever produces proofs for truth statements, this simulator then could decide the truth of statements. Even if it only produces proofs for true statements. In particular, because the simulator is efficient. The simulator could decide the truth of statements efficiently. Why is this bad? Any ideas? So let's think about what sort of statements we're trying to prove in zero knowledge. The example I gave over here was I'm trying to prove in zero knowledge that two group elements have the same discrete logarithm. What would the problem be if we could produce a simulator that could decide this efficiently without knowing the witness? Yeah, what do you mean by that? I didn't quite understand what you said.
So then if you were given an element and you wanted to compute its logarithm, you could just try pairs or something and see.
Yeah. Yeah. I mean, you're on the right track, right? The point is that this is going to violate hardness assumptions. I think the specific example you provided is somehow not a big deal because the space of powers is not polynomially bounded anyway, so this is not going to efficiently break discrete logarithm. But the problem is that we still conjecture that a lot of decisional problems are hard. So for example, decisional Diffie-Hellman, right? We assume that given G to the A and G to the B, you can't tell G to the AB apart from G to the C for a random C. So this would somehow not make sense a lot of the time because when doing zero knowledge proofs in practice, we assume this exact decision problem is hard. So this definition or this proposed idea for a definition doesn't make any sense, is the upshot. Okay, so how are we going to get out of this? The idea is, let's think about how we defined knowledge soundness. The knowledge extractor was supposed to be able to produce a witness by interacting with the prover, but this doesn't seem to make sense because the witness is supposed to be secret. So how do we get out of it with the knowledge extractor? Well, we let the knowledge extractor cheat a bit, right? What I mean by cheating is it has rewinding access, right? The knowledge extractor was allowed to run an interaction with the prover until it gets a challenge and response, then rewind to the same commitment, get another challenge and response. So the knowledge extractor cheats a little bit, and that's how it manages to extract the witness without breaking zero knowledge. We're going to let the simulator cheat as well in the right way. Okay, so how are we going to let the simulator cheat? Well, we're going to use the same idea. We're going to say that the simulator is allowed to rig the random oracle, okay? We're going to assume, okay, we're going to start by assuming that the non-interactive proof uses a random oracle, sorry, a hash function H. I'm going to say it's from some universe to the challenge space C, okay? Talking about zero knowledge, so we're going to talk about the challenge space. And this is fine to assume because what we're going to do is we're going to prove that the Fiat Chameleon transformation is zero knowledge. So of course this does use a hash function and it's used in the form of generating challenges. So this is okay. In particular, this is supposed to be finite. Otherwise we have issues with uniformly sampling from an infinite set, right? So I'm just gonna assume it's finite. Okay. First definition for today: a non-interactive simulator. Given a non-interactive protocol, it's an interactive probabilistic algorithm, and it's going to respond to two kinds of queries. So this is going to get a little bit weird, but bear with me. So a non-interactive simulator for a non-interactive protocol it's an interactive, efficient algorithm. The simulator always has to be efficient. And it responds to two kinds of queries. I'll clarify what I mean by that in a minute. Okay. So again, for concreteness, if you want to think of this as this interactive algorithm as being a Turing machine, what I really mean is you can send it two kinds of message, right? Then the messages have a certain structure. And if it starts running and its input tape doesn't match either of these messages, it just immediately halts again. Otherwise, it evaluates the query. And hopefully you can kind of see how this could be modeled. It's not terribly interesting for our purposes to go into detail, but that's what I mean by two kinds of queries. It expects one of two forms on its input tape. If it gets neither, it just does nothing. Okay, so the first is called a justified proof query. And this is just going to be a statement and a witness. It responds with a proof. Some pi in the proof space. The other type of query it expects is, sorry, I am reading the wrong thing. I didn't think this made sense. The simulator asks for unjustified proof queries, right? Because we are simulating an interaction with the prover, so we don't actually have the witness. So you can ask the simulator for a proof, and this is just a statement in the statement space, to which it responds with the proof. Some proof in the proof space. It also responds to a random oracle query. Okay, so you give me some u in the hash function's universe, and it's going to respond with some challenge. Okay, so our simulator, not only does it produce proofs given a statement, it also produces random oracle. It also evaluates random oracles. So why does this make sense? Well, we said that the simulator is supposed to be able to rig the random oracle. So the idea is that a verifier that is trying to get knowledge out of the interaction is going to use the simulator's random oracle as part of that. And the simulator can make things match up so that by using its simulated random oracle, the verifier can't possibly learn anything. It can't possibly tell that it's fake. The verifier is using this random oracle, right? Remember that the verifier, as part of its procedure in the Fiat Chameleon transformation, uses this random oracle. So the simulator is going to cheat with its fake proofs by making the verifier think they're legit proofs. And that's how we define non-interactive zero knowledge. Again, this is a weird definition. This is not supposed to somehow be obvious. So let me try to explain what universe we're working in. We're going to do a reduction of sorts, but we're going to sort of step into this common crypto model, which is the real world simulated world model, okay? The idea is any verifier who's interacting with either a real prover or the simulator cannot tell which world it's in. And we say then it's zero knowledge, right? Because the simulator doesn't even have the witness. So if the verifier can't tell whether it's talking to a simulator or not, well, the simulator doesn't, so the verifier can't possibly learn anything. That's the logic. So we're going to ask that two worlds are indistinguishable. First is the real world. A verifier gets real proofs, right, which come from gen xw, and real random oracle evaluations. Okay, so we're working with the random oracle model. This hash function we say now is a random oracle, and in the real world, the verifier can query an actual random oracle that does indeed follow this uniform random distribution. And the simulated world, where the verifier gets fake proofs, and uses the random oracle via the simulator. Okay, and we're going to say any efficient such verifier, okay, so it makes polynomially many proof queries and random oracle queries. We're going to say that any such verifier cannot tell these two apart, and that counts as non-interactive zero knowledge. So I have a slightly long definition coming up. I apologize for that. We say interactive algorithm A is a NISC adversary, non-interactive zero knowledge adversary. For a non-interactive protocol, nope. I'm going to say it like this. If it always makes one of two queries. So again, for completeness' sake, you could imagine that our interactive algorithm is a Turing machine with an input and an output tape, and our NISC adversary only ever puts things on its output tape of one of the two forms. Okay, it's going to ask for justified proofs. Which are xw in x times w, and random oracle evaluations. And that's going to be a u in u. Okay. Given a non-interactive protocol, I'm going to fix a non-interactive protocol, gen check, or I phrased that wrong, but that's fine. It is non-interactive zero knowledge. Okay, if there exists a simulator S such that the transcript distributions of the two worlds are identical. By world, I'm going to use the word experiment. By an experiment, I mean you've got your adversary, you've got your simulator, you've got your proof. They interact, and then you look at the transcript. That's an experiment. It's not meant to be a formal word. Experiments are indistinguishable. Okay, and remember, indistinguishable just means no efficient algorithm can tell them apart, except with negligible probability. Okay, simulated world. Oh, sorry, I should start with real world to be consistent. So in the real world, at the start, we choose an oracle, uniformly at random. And we answer a proof query by just running the proving algorithm. And we answer the oracle query with, you guessed it, the result of evaluating the oracle on U. That's the real world. Simulated world. We do not choose a random oracle function. We just answer xw by evaluating or by querying s with x. Okay, so the simulator does not get the witness, it just gets a statement, and it's going to produce a proof which we give to the adversary. And we answer u by querying s with u. Okay, so these worlds are of a fundamentally different character, right? In the real world, we have a fixed random oracle function, and we're doing the things we're supposed to. We're not running any interaction. Okay, we're just the adversary is trying to interact with the environment, so to speak, and it's being answered by non-interactive stuff. In the simulated world, it is being answered by an interactive thing that has state, right? By a interactive algorithm. So these are fundamentally different character. I just saw a comment, Will.
We're talking about foundations. Sorry, so rude. But
Yeah,
keep going. Yeah.
yeah. The foundations are definitely shaky. We can have that discussion offline.
No, sorry. The foundation seminar. No. I meant the foundation seminar. I'm being incredibly rude right now. So I apologize.
No worries. No worries. No worries. Let's carry on then. Okay. Any quick questions about exactly what the hell I just defined? So the picture is, right, there's an adversary box. In the real world, it's interacting by I'm just evaluating functions, right? Evaluating computable functions. In the simulated world, the adversary box is talking to a simulator box. So that's the fundamental difference between the two. And I'm very sorry about this. I need a technical definition. So it is not true that a special honest verifies zero knowledge Sigma protocol is NISC. That is not true. You need an extra assumption. The extra assumption is a Sigma protocol has unpredictable commitments. I mean, this is dead simple, right? Any interaction produces any specific commitment with negligible probability. For all t hat in the commitment space, which I'm going to write as just big T, PR T equals T hat in a transcript is negligible. Okay, really simple. It just means you can't predict which commitment it's going to produce. And we'll see why this technical assumption is necessary. Okay, and now we have our result. Sigma, a special HVZK, HVZK Sigma protocol with unpredictable commitments. Pi. Let pi be one of these. We need some lasso tool, Dan. Produce. I'm going to say produces music. A music protocol fs pi. Okay, so we do the Fiat Chameleon transmission to our protocol, and it's going to be NISC with this assumption in the random oracle model. Okay, proof. All I have to do is produce a simulator, right, and prove that it and prove that you can't tell whether you're talking to it or not. Air quotes all. So the simulator does this. Use some kind of pseudocode. It gets, what do I have to define? It's allowed to do some kind of setup, right? It's allowed to sort of, on its first invocation, do some computation. And then I just have to define what it does on each query, right? So setup. We're going to choose, M is going to be a map. And I'm going to assign it to the empty map, which is of type x times t to c. Okay, so the idea here is I'm going to remember which statement commitment pairs I've been queried on. Okay, so and this in the Fiat Chameleon transformation plays the role of you query the random oracle with statement commitment pairs. Okay, so I'm just going to choose, and I'm going to start with an empty map. Think of it like a dictionary, if you like. And on the ith justified proof query, which I write as xi. Here's what it does. First, we choose a uniformly random challenge. And we use the special honest verified zero knowledge simulator to produce a commitment and a response. I call this sim1, xi, comment, sim1 from special hvzk. Okay, so I'm choosing a random challenge and then I'm simulating a transcript, which I'm allowed to do by assumption. Now, it's possible that the statement commitment pair has already been queried. It's possible that the random oracle has already been queried for this statement commitment pair. If it does, we're going to have to be consistent, right? If it gets queried later, we're going to have to make sure that we answer with this challenge in particular. Sorry, I bungled that. Let me try again. So I've got a statement and a commitment, and I've been given a statement, and I'm going to return a commitment. Now I have to be consistent if I'm later queried with that statement and commitment, right? I can't give you a different challenge that doesn't stack up with the response. I have to stay consistent. So if this particular statement commitment pair is not in my map, I'm going to just add it to my map. I'm very sorry to any type theorists in the audience. I'm going to pretend that functions are their graphs. Okay, so I'm going to remember that if I'm queried with this statement and this commitment, I'm supposed to give you this challenge. And then I just return the commitment response pair. I've run out of space. I'm going to go on to the next thing. Okay, so now I have to say what happens when I get random oracle queries. And for the sake of Fiat Chameleon, the random oracle queries are statement commitment pairs. I use a hat because this may not be the same xiti that I saved on the unjustified proof query. So let's not get confused by that. Okay, so now it's really simple. If I haven't already produced a challenge for this statement commitment pair, I'm going to do that. Otherwise, I'm just going to return the one that I've already saved. So if I haven't already been queried with this challenge commitment pair, statement commitment pair, I just generate one uniformly at random and add it to my map. And now I just return whatever's in my map. Okay, that's it, that's the simulator. So let's try to think about this. How could you tell these two worlds apart? The way that you tell that you're talking to a simulator is you catch it equivocating, right? What do I mean by that? Well, it's on the one hand, if you look at the first board, on the one hand, it's supposed to be generating challenges that match up with the responses and commitment it gives. But on the other hand, it doesn't control what statement commitment pairs it gets queried on. So you could catch the simulator, you could tell that you're talking to the simulator if the following happens. If you query it with a statement and a commitment, and then you get a challenge, and then later you also query it with that statement, and it returns a commitment and a response that don't make sense for that challenge, right? Because the non-interactive verifier is going to generate the challenge according to the random oracle, and here it generates the pairing differently, right? It doesn't just choose. So the only way you can catch it is if you guess a commitment in advance, or if the commitment just happens to appear twice. Both of these are negligibly unlikely, so you are unlikely to catch the simulator. Okay.
Sorry,
How do you catch the simulator?
I lost you at the end there. What the commitment appears twice. Can you describe that case again?
Mm-hmm. Yep. So how do I catch the simulator? Well, what I'm going to do is, let me think about this carefully. So our simulator is getting its commitments from the interactive simulator, right? That means that you give the simulator a statement and a challenge, and it produces some commitment, and there's some according response. Now, what could happen is I give the interactive simulator two different challenges. It happens to produce the same commitment twice, but the response is different because the challenge is different. Okay. So the first way is the interactive simulator produces the same commitment twice. For different CI and RI. Can you think, how does this mean that you've caught the simulator? You can tell that you're talking to the simulator. Well, because the verifier won't accept both challenges. Because it generates its challenges from the random oracle, from the simulated random oracle. Okay, so what could happen is the simulator produces the same commitment for different challenges, and then the verifier, to get its challenge, asks the simulator to produce the challenge for that commitment, and the simulator gives only the first challenge, so the verifier won't get the second challenge, so it won't accept the second response. Did that make sense, Dan?
Yeah, thanks. I got it, I think.
Yeah. Well, the other way is much less interesting. The other way you might catch it is if you guess a commitment in advance. Okay, so I've got a statement. I'm going to ask for an unjustified proof, but first I'm going to guess what commitment it's going to commit to, query the random oracle, it produces a challenge, and then I send the unjustified proof, and it's going to produce a different challenge, right? Because it's just choosing challenges uniformly at random. So the idea is you have xi, you guess ti, query the arrow with xi, ti, you guess ci, query the proof, query a proof, which with overwhelming probability is for a different challenge. So these are the only two ways that you can catch the simulator. In every other case, the transcripts are exactly identical, but these are both negligibly likely. By the unpredictable commitments assumption. So that's why we need this assumption. That's it. So we have this slightly strange condition that we're going to need to digest in the interim, simply because our previously accepted definition of zero knowledge doesn't make sense in the non-interactive context. And we have proven that with our Fiat-Shamir transformation, such a protocol does achieve, a Sigma protocol does achieve non-interactive zero knowledge. So now we know how to make non-interactive zero knowledge existentially sound proofs, right? We take some Sigma protocol, do the Fiat-Shamir transformation, and we are done. We can prove a pretty big class of statements this way. But this isn't the be-all, end-all of zero knowledge. First, because some statements are just, it's unclear how you would translate it into the Sigma protocol framework. Second, because we don't know how to produce a Sigma protocol for any proof. Sidebar, this is sort of possible. Third, because even if we could produce a Sigma protocol for every proof, it might not be terribly efficient, right? We might want to make the proof small, easy to compute. So we want to look at other ways to do zero knowledge. I'm open to ideas for where to go next, but I think next time it makes sense to get started on the proof that every NP relation has a zero knowledge proof, and we'll go from there.